Welcome everybody to this session. I have now a mix of overview slides and also technical slides. I try to keep it very abstract and go over the technical slides with a high level. You find a lot of these figures again in the documents that Peter pointed out on his last slide. So if you have questions either today then or just go to the literature that we also provide to get the details again. So when we want to talk about solving IT+OT convergence, let's first have a look at what that actually is. We have three different kinds of deployments that we can think of. And the left one you have seen in a similar form on Peter's slide when he showed on the left side that you have field buses on the bottom. And then the controller to the cloud or the edge talks OPC UA. That is something that you already see a lot today, where all the PLCs have OPC UA client server available. The downside there is the PLC always needs to translate the data. So we want to get towards converged networks, open networks, where you directly can access all the data. You can see that labeled with mixed deployment in the middle. And with the colors, you also see that we now mix green and orange. Orange just stands here in this example for any field bus, industrial protocol. Green, we just selected any number, any color, now stands for UAFX. And you see on the wires, they are merged. On the same wire, you use different protocols, different application types, and you mix the network. In the past, that was not very good enabled by a lot of these field buses because the networks just were designed to be isolated. So now we need mechanisms that enable us this convergence, and we'll talk about that in a second, mainly under the term TSN. And also on the right-hand side, you see that with UAFX over TSN, we will be able to also fully go on UAFX if you want that. And as Peter mentioned, we always have the direct connection in any of the two right scenarios from the end devices directly to the edge or cloud, but also between PLC and end devices, so the controller to device, controller to cloud, but also you can connect the controllers, controller to controller here. So if we look at TSN, TSN is always a broad term. Let's have a look at what we actually want to use here. 6802 is a standard defined in the IEEE, IEC IEEE 6802, and it defines a profile for industrial automation. And from this whole big cloud term, a TSN, it selects a few different things. First, it selects a few mechanisms to give you guarantees. It has certain QoS features in there, scheduled traffic, frame preemption, and strict priority, for example. It also standardizes a few things on how to do disciplining, VLAN retaking, reprioritization, and rate limiting. And also, it looks at reliability. And in some of the existing field buses, you have seen certain forms of that already, but now it's the first time that we have a unified set of these features where people can build on. So it fully is based on IEEE ITF specifications. It covers QoS, robustness, reliability, and certain other things that you just need in a network to openly work with these networks. What do we now in OPC Foundation do with that? We define facets. And as Peter mentioned, in part 84, and that's the most important one where you first want to look in if you want to build a product, there you find these facets. And with these facets, we then link to the different features that you need to implement. Important now for this discussion are the facets on the bottom, where we look at the network, so the bridges, the switches inside the devices. We defined three different facets, and from the whole set of what 6802 talks about, we just created three different groups that include each other. So base facet is just a very simple managed bridge. Then we have advanced, which adds a few QoS features like frame preemption, and then the full facet is basically similar to what 6802 defines. And now you can create different kinds of products for different kinds of applications. And we also do not want you to just be able to connect full facet with full facet. We want you to be flexible, maybe have certain parts of your factory already for really tough quality of service requirements with full facet equipped. And then other areas where you just don't need it, where you don't have a lot of other traffic, the application just doesn't need it, you can also take the lower facets. And by that, you are very flexible in what you do. And to showcase that, and that is a graphic that you also find in the literature, a little more explained, I'll roughly go over that here. We defined the graceful degradation. What you see is that on the left, we have a network segment that is FX advanced. That's the middle of these three facets that I just presented, because most devices here are yellow. And then if now this device on the bottom here wants to talk to some device over here, it can never get more quality of service than it has itself. And if you look at what is in between, nothing of a lower quality of service must be available. So here, for example, we have a full FX, which has a lot of quality of service features. And then here towards the edge, you always get a little less. And so here, when we take that communication path, we can achieve yellow. And the same would here be for blue, because here we have a blue network segment, so we can only achieve the base. But also it enables you to just integrate legacy devices that are not one of these facets. Of course, you achieve less quality of service features here, or quality of service capabilities, but we want to offer this flexibility. Now let's have a look at what we do actually at the end device. When you program your here two controllers, controller A on the left side and controller B on the right hand side. There is an engineering workflow that we define in UFX to get to this stage. And I'll now focus on what happens when you power on the devices and they should really start the communication. You always have a connection manager. The connection manager is the key that enables that we have the communication. And that connection manager has all the connections programmed in with here certain quality of service that was selected by the application engineer. The connection manager now connects to all the controllers involved in the communication and then creates the actual pub/sub configuration. So that is, as Peter said before, we build on top of what is existing. We are not defining something new for the transport. We just define on a way how to configure what is already existing from how an engineer normally operates with a PLC. So now we have our pub/sub configuration that has, for example, here the quality of service category priority. We only want to do priority-based QoS, so we want to order the different applications based on their priority and just specify which one is more important. And the first label that we define is green, that is for cyclic unsynchronized traffic. And now when the pub/sub connection actually starts sending traffic, it goes through a mapping table that is part of the base specification in OPC UA. And it uses the mapping table to determine the actual priority values to use on the wire. And then you have a network configuration that can differentiate different priority values, and you get the quality of service that you need. So in UAFX C2C, so what is already released, we support the enhanced prioritization. And with that, you already have advanced QoS in your network. And now I made a start to that because we just didn't define it on our own. We also work with the 6802 together, that they adopt the mechanism in their standard as well, such that this prioritization mechanism with the mapping table is available to all the protocols that will build on 6802 later. And with that, you can not only prioritize pub/sub traffic in here, but any other traffic that you have in your network, any field bus, you can now combine that and use the same prioritization mechanisms to align your network configuration. If we look at the future, where we have maybe more advanced quality of service requirements with specific deadlines, we add a new entity here that comes from 6802. But we define that now somewhere in our engineering process, and that is now one example where the connection manager does this dynamic reconfiguration or resource allocation. The connection manager has all the requirements inside. It knows exactly how the end devices want to behave. So it tells the central entity how the devices want to behave, what they request from the network, and that can either reconfigure the network or can just assure that the network already fits to that. And then we have exactly the same process. Now here you see that we have another entry in our mapping table, now with deadline. And I just invented now the label motion. We didn't specify any further labels yet. And for example, with the motion, you also specify a deadline when the data should be on the other side. The network is configured to do exactly that for specifically the PCP value 7. And so now our end devices can automatically send the data with PCP 7. And with that, we can even, for different types of pub/sub traffic, different types of UFX traffic, we can differentiate them in the network and can use the same network for different types of traffic and use the network efficiently. So in C2D release, we add additional resource reservations, specifically for bandwidth, latency, and deadline. That's what we currently work on. And to conclude my talk, I want to briefly point out our demo that we have available. Go by the OPC booth and have a look at what we have there. We already showcased the C2C release QoS with the prioritization, and we also have a short outlook on the C2D quality of service ideas with the resource reservation. Thanks, everybody.